Hey YouTubers, welcome to the Cyber Overwatch channel. I am Pragmatic One. In this video, I will be doing a walkthrough of TryHackMe's Lookup vulnerable host. I will provide a walkthrough of reconnaissance through post-exploitation. This will include performing port scanning, service enumeration, user enumeration, password brute forcing, command injection, path hijacking, and privilege escalation. If you find this content informative and you are interested in cybersecurity, please like and subscribe to the Cyber Overwatch channel. Also, for more free content, please regularly check back on www.cyberstack.com. Lookup is a vulnerable host created by TryHackMe. It's designed to simulate security weaknesses and give you hands-on practice with common attack vectors. This host demonstrates several critical vulnerabilities. Let's break down the attack surface using the MITRE attack framework. T1078 valid accounts. The login page suffers from username enumeration. The web application returns different error messages depending on whether the username exists in the system. This information disclosure allows attackers to build a list of valid usernames before even attempting password attacks. T1110 brute force. Once valid usernames have been identified, the attacker can focus on password attacks using tools like Hydra and FUF with common password word lists. T1190 exploit public-facing applications. The host runs LFinder version 2.1.47, which is vulnerable to CVE-2019-9194. This is a command injection vulnerability in the PHP connector that allows unauthenticated remote code execution. The flaw exists because user-supplied file names aren't properly sanitized before being passed to the exif-tran utility. T1059.004 command and scripting interpreter Unix shell. The LFinder vulnerability allows an attacker to inject arbitrary shell commands through manipulated file names. An attacker can leverage this to establish a reverse shell and gain initial access to the system. T1548.001 abuse elevation control mechanism, set UID and set GID. The system has a custom SUID binary PWM located in the /user/sbin directory. SUID binaries run with the permissions of the file owner rather than the user executing them. When improperly secured, they become prime targets for privilege escalation. T1574.007 hijack execution flow, path interception. The PWM binary calls the ID command without using an absolute path. By creating a malicious ID binary in the /temp directory and prepending the /temp to our path variable, the attacker can hijack the execution flow and escalate from www-data to the think user. Alright, I've deployed the Lookup host and it now has an IP, as can be seen on the TryHackMe dashboard. First things first, I need to understand what I'm dealing with. That means port scanning and service enumeration. I want to know what services are running, what the versions are, and what attack vectors are available. Nmap is always my go-to for this phase. It's the industry standard for network discovery and security auditing. I'll execute the following commands shown in the CLI to kick off the initial scan. But first, let me break down this command. -lowercase uppercase s performs a SYN scan or stealth scan. -lowercase p scans all 65,535 ports. -A enables OS detection, version detection, script scanning, and traceroute. -T4 sets an aggressive timing template for faster results. The Nmap scan has completed and I've got some interesting results. 2 ports are open. Port 22, SSH. This is a secure shell service for remote administration. OpenSSH 8.2 P1 is fairly recent and doesn't have any critical public exploits, so this probably isn't my entry point. However, if I find credentials later, we can use this for stable access. Port 80, HTTP. This is a web server running Apache. The scan shows a redirect to http://lookup.thm, which tells me that the web application is using virtual host routing. The OS detection shows this is an Ubuntu Linux system based on the CPE data. The banner information and service fingerprints all confirm we're dealing with a Linux target. The web service on port 80 is immediately interesting because of the redirect. Let's investigate. I opened Firefox. Let's try to browse to the target host's IP. When I try to browse directly to the target host IP, I'm immediately redirected to lookup.thm and hit with a server not found error. This is a good indication of virtual host configuration. Here's generally what's happening under the hood. Apache is configured with name-based virtual hosting. When you hit the IP directly, Apache looks at the HTTP host header in your request. The server configuration only responds to requests for lookup.thm, so it sends a redirect. Your browser then tries to resolve lookup.thm, but it has no DNS entry. It's just a local host name configured on the target host. The solution is simple. I just need to map the DNS name to the IP in my etc/hosts file. This file acts as a local DNS override, mapping host names directly to IP before your system queries any DNS server. I right-clicked and selected View Page Source so that I could review the page source line by line. I'm looking for several things: commented out code that might contain old functionality or credentials, hidden form fields with interesting values, JavaScript files that might contain API endpoints or business logic, framework identifiers that could point to known vulnerabilities, and metadata that reveals development patterns or file structures. Unfortunately, this application is pretty clean. No obvious information disclosure in the source. Time to move on to active enumeration. Since manual analysis didn't yield results, I'm switching to directory brute forcing with FUF. This tool is incredibly fast and efficient for web fuzzing. I'll run the following FUF command shown in the CLI. Here's what each parameter does. -u is the target URL with fuzz as the placeholder that gets replaced with each word list entry. -w points to the word list I'm using directory list 2.3 medium from seclists, which contains about 220,000 common directory and file names. -t sets 500 concurrent threads. This is aggressive and makes the scan much faster. -r automatically follows redirects, which is crucial since some directories might redirect to login pages or other locations. Despite an aggressive word list, the FUF scan came up empty. It looks like I'll need to dig deeper to find a new vector. When directory fuzzing fails and the page source is clean, we need to test the application's functionality directly. Burp Suite is a de facto standard for web application security testing. It acts as an intercepting proxy sitting between the browser and the target application, allowing you to capture, inspect, and modify HTTP traffic. I've configured my browser to proxy through Burp Suite. I've also set the scope to Lookup.THM, so I'm only capturing the relevant traffic. The application has a login form, which is interesting from an attacker's perspective. Login forms are often vulnerable to several attack types: username enumeration, SQL injection, authentication bypass, and brute force attacks. Let me test the basic functionality first. I'll submit a request with test as credentials and see how the application responds. The application returns wrong username or password. This is a generic message, which is actually good security practice because it doesn't tell you whether the username exists or not. However, let's see if there are any subtle differences in the responses that might leak information. I've captured the login request in Burp Suite and I'm sending it to Intruder. For those unfamiliar with Burp Suite's architecture, let me explain what Intruder does and why it's so powerful. Intruder is essentially an automated attack framework within Burp Suite. Intruder is an advanced fuzzing engine that automates customized attacks against web applications. Here's the workflow. Number 1, capture a baseline request. Intercept a normal request that you want to modify. Number 2, mark injection points. Identify which parts of the request you want to fuzz. Number 3, load payload sets. Choose your attack data, usernames, passwords, SQL injection strings, etc. Number 4, configure attack type. Select how payloads are inserted. Number 5, launch and analyze. Send thousands of requests and compare responses to identify anomalies. Intruder is incredibly versatile. Here are some practical use cases: credential stuffing and brute force. Test authentication endpoints with lists of usernames and passwords. You can identify valid accounts, test password policies, and find weak credentials. Parameter fuzzing. Inject malformed input, special characters, boundary values, and edge cases into parameters to trigger errors, bypass validation, or cause unexpected errors. Injection testing. Systematically test for SQL injection, cross-site scripting, command injection, and other injection flaws by inserting payloads and analyzing responses for signs of successful exploitation. Insecure direct object reference enumeration. Increment numeric IDs in URLs and parameters to discover accessible resources you shouldn't have access to. Session analysis. Test session tokens for predictability and randomness issues or brute forceable patterns. Rate limiting assessment. Verify that security controls are properly throttling requests to prevent abuse. Intruder offers 4 attack types, each suited for different scenarios. Number 1, Sniper. Single position attack. It uses one payload list and iterates through it, replacing one position at a time. Perfect for targeted testing of individual parameters. Number 2, Battering Ram. Multiple position, single payload list. The same payload value is used in all positions simultaneously. Useful when you need synchronized values across multiple fields. Number 3, Pitchfork. Multiple positions, multiple payload lists. Each position gets its own payload list and they iterate in parallel. First entry from list 1 with first entry from list 2, etc. Great for testing paired data like username and password combinations. Number 4, Cluster Bomb. Multiple positions, multiple payload lists. Test every possible combination of payloads across all positions. Generates the most requests but provides comprehensive coverage. For this attack, I'm using Pitchfork because I want to test the username and password pairs efficiently. I've marked 2 positions in the request. Position 1, username parameter. Position 2, password parameter. For payload set 1, I have payload position set to 1. The payload type is set to simple list, which means intruder will iterate through each entry one by one. I have loaded the names.txt word list from sec lists. This contains thousands of common first names and usernames. For payload set 2, I'm using the RockU password list. This contains the most commonly used passwords found in data breaches. Again, using simple list as the payload type. I click the start attack button and intruder is now sending requests. Each row represents one request to response pair. I'm monitoring the status codes, response lengths, and response times. I analyze the results as the attack continues to run. Initially, everything looks pretty uniform. All requests return 200 OK status codes. Most responses have a length of 336 bytes. All responses with 336 bytes contains the error message, wrong username or password. At first glance, this looks like good security implementation, consistent responses that don't leak information. Let's dig deeper. This is where things get interesting. When I sort by response length, I notice 2 payloads that stand out. Admin, response length 301 bytes, error message, wrong password. Jose, response length 301 bytes, error message, wrong password. This is a critical information disclosure vulnerability. The application is revealing whether usernames exist in the system by returning different error messages. Wrong username or password for usernames that don't exist, wrong password for usernames that do exist, but the password is wrong. This is textbook username enumeration. I've now confirmed 2 valid accounts, admin and Jose. Now, normally I would continue to brute force in Burp Suite to find the passwords, but there's a problem. Burp Suite Community Edition throttles intruders' performance. It's intentionally slow to encourage users to upgrade to the professional version. For credential brute forcing with large word lists, this makes it impractical. So let's pivot to FUF, which has no such limitations. FUF isn't just for directory brute forcing, it's an excellent tool for parameter fuzzing as well. Let me break down the commands shown in the CLI. -W is for the word list, -U is for the target URL, -X uses the post method for submitting data, -H sets the proper content type header for form data, -D is what will be in the post data body, fuzz in all caps is my injection point where each password will be tested, -T uses 100 concurrent threads for speed, -FW filters out responses with exactly 8 words. This should filter out the wrong password responses and hopefully only show me successful logins. Running the FUF command, it looks like password 123 was detected as a possible password for the Jose account. Let's test these credentials against the login form. After clicking login, I'm redirected to files.lookup.thm and hit with another server not found error. This is a similar message I received when I initially tried to go to lookup.thm. In this case, I will need to add files.lookup.thm to my hosts file. I ran the following echo command shown in the CLI to add files.lookup.thm to the /etc/host file. After updating the host file and refreshing, I now have access to the authenticated area. I can see what appears to be a file manager interface with several text files listed. I click through the available files to see what information is exposed. One file contains the credentials I already know, Jose, password 123, confirming I'm on the right track. The other files don't contain anything immediately useful, appearing to be mostly placeholder text files or benign data. The help section reveals the application is running Lfinder version 2.1.47. Knowing the exact version of software is critical for exploitation. Let's see if this version has any public exploits. I'll run the following searchsploit command shown on the CLI. Searchsploit is a command line interface for exploitdb. It searches local copies of thousands of exploits in proof of concept code. Reviewing the results, I see some promising exploits. The Lfinder 2.1.47 PHP connector command injection seems like the best option to try. This is the exact version of the target host. Command injection vulnerabilities are extremely serious because they allow arbitrary code execution on the server. I'll give this exploit a shot. When I ran the searchsploit command shown on the CLI, the output provided some useful information. The -M flag mirrors or copies the exploit to my current directory. Searchsploit provides useful metadata. The exploit DB URL links to the full write-up, the local path where the exploit is stored on the system, and the CVE-2019-9194, the official vulnerability identifier. The exploit script 46481 is now in my downloads folder, but before I just blindly run it, I need to understand what it does. Never run exploit code without reviewing it first. There are several reasons for this. Number 1, security. Malicious exploit code could compromise your own system. Number 2, understanding. You need to know what the exploit does to use it effectively. Number 3, modification. You need to customize it for your specific target. Number 4, dependencies. You need to know what requirements it has. So let's review the code. The header provides critical context. This affects LFinder version up to and including 2.1.47. Also provides the publish date, usage instructions, as well as who discovered and reported the vulnerability. This payload is cleverly constructed. Number 1, payload construction starts with a legitimate looking file name, secsignal.jpg. Number 2, the semicolon command separator allows command injection. Number 3, echo outputs the hex encoded reverse shell. Number 4, it pipes to XXD, which converts hex back into binary. Number 5, redirects output to create a PHP file. Number 6, ends by echoing the file name to avoid errors. The usage function checks if the correct number of arguments is provided. If not, it prints the usage instructions and exits. The upload function handles the upload, constructs a multi-part form data post request, sends the malicious file name as the upload, parses the JSON response to extract the file hash, returns the hash for use in the next step. The image rotate function triggers the vulnerability, sends a request to rotate the uploaded image, uses the file hash from the upload. The mode equals rotate parameter triggers exif_tran. Exif_tran receives my malicious file name and executes the injected command. The shell function provides an interactive shell that attempts to access the uploaded PHP reverse shell. If the script is accessible, status code 200, it enters a loop where it takes user input and sends it to the C parameter. The PHP script executes the command and returns output. If the script is not accessible, it prints a message indicating that the site is not vulnerable. The main function calls usage function to check arguments, extract the URL from the command line arguments, uploads the malicious image, runs the payload, and calls the shell function to gain a shell. For my purposes, I wanted to use a PHP reverse shell that connects back to my listener. Instead of using the default payload, I used a PHP reverse shell one-liner and encoded the web shell in hex using a tool like Crypty. The script also requires a JPEG file named secsignal in the same folder as the exploit script. I simply Googled JPEG image to download one. Choose whatever method works for you. With the JPEG downloaded, I started my netcat listener using the following command shown in the CLI. With my netcat listener running, I'll execute the exploit using the following command shown on the CLI. Based on the output, it appears that the exploit script uploaded the JPEG successfully and it states it's running the payload. When I look at my netcat listener, I can see that it shows a session was created as the www-data user. Now that I have a session, let me navigate the target host and look for low-hanging fruit. I browsed the PHP folder, but I found nothing of interest. I ran the following command shown on the CLI to change directories to the /home folder to see what user accounts exist on the system. The output shows 3 user accounts: SSM-user, the AWS Session Manager account, Think, and the Ubuntu account. I navigated to the Think user folder using the command shown in the CLI to view the contents. Right away, I see user.txt file containing the first flag and an interesting file called .passwords. Unfortunately, after running the cat command, I cannot access either user.txt or .passwords because the www-data account receives a permission denied message. I need to find a way to escalate my privileges. The next step involves automated host enumeration using linpeas. I launched an HTTP server to transfer the linpeas script to the target host. With my HTTP server running, I'll run the following wget command shown in the CLI to upload linpeas to the target host. Based on the output, linpeas uploaded successfully to the target host. With linpeas on the target host, I will run the following linpeas command shown in the CLI. Linpeas is currently running and it can take some time. I'll need to wait for the results. Under the files with interesting permissions suid check section, the output notes an unknown suid binary called PWM. I also noticed that the output points to /home/www-data/.passwords, but I only saw the .passwords file in the Think user account folder. Interestingly, the output notes that PWM is able to impersonate p-error. Based on my research, it indicates that there is no absolute path documented for the program that PWM executes. When I run the PWM file, it appears PWM performs the following. 1. Runs the ID command to check the current logged in user. 2. After ID identifies the user as www-data, PWM attempts to locate the .passwords file in the www.data account's home directory, but can't find it. Based on the logic, PWM appears to be some kind of password manager. Since PWM doesn't appear to be a normal Linux program, I decided to transfer it to my system for further analysis. I ran the following netcat command shown on the CLI from the target host to copy the file. Before executing netcat on the target host, I made sure to run my netcat listener on my system using the following netcat command shown in the CLI. After executing netcat on the target host, I see a session was created. I ran ls and verified that PWM had transferred successfully. With PWM on my system, I ran the strings command. The strings command extracts all printable ASCII strings from a binary file. This is useful for reverse engineering because it can reveal hard-coded passwords or keys, error messages, command strings, file paths, and function names. Based on the output, PWM executes the ID command and reveals the binary's behavior. Number 1, it executes ID without an absolute path, just ID, not /user/bin/ID. Number 2, it parses the username from the ID command output. Number 3, it constructs a path /home/%s/.passwords, where %s is a variable for the user account. Number 4, it reads and displays that file if it exits. The vulnerability here is the ID is called without an absolute path. This means the binary relies on the path environment variables to find the ID executable. We can exploit this through path hijacking. Now I need to test whether I can abuse the lack of path requirements when running PWM. I created a fake ID file and stored it on my system to upload to the target host via wget. I ran the wget command shown on the CLI to upload the fake ID file to the target host. As can be seen by the output, it has uploaded successfully. With the fake ID uploaded to the target host, I ran the following command shown on the CLI to make the ID file executable, then verified the permissions. In order for this to work, I need to check the current path environment variable. I ran the following echo command to view the current path. Based on the results, I'll need to add /temp to path in order to successfully execute path hijacking. Now I'm hijacking path by prepending /temp to the beginning. This is critical because by putting /temp first, when any program tries to execute ID, the system will first find our malicious version in /temp before it finds the real one in /user/bin. The export command makes this change active for the current shell session. I chained the export command with echoes $path to verify the modification was successful. The output should now show /temp at the very beginning of the path. I executed the PWM binary again, but this time with our hijack path. Here's what happens. 1. PWM executes ID without absolute path. 2. The system searches path directories from left to right. 3. It finds our fake /temp/ID first and executes it. 4. Our fake ID outputs UID equals 1000 think, GID equals 1000 think, groups equal 1000 think. 5. PWM parses think from this output. 6. PWM reads /home/think/.passwords with SUID privileges. 7. The contents are dumped to our screen. The output shows a list of passwords from the .path.passwords file located in the think user's home directory. This is valuable data, so I've saved the output to a file called output.txt. This gives me a word list I can use for further attacks, specifically a dictionary attack against the SSH service I identified earlier. I ran the cat command on output.txt to verify the passwords were exported. Based on the output, it was successful. Now I need to transfer this file list back to my system. I start another netcat listener using the following command shown on the CLI, redirecting the incoming data to a file called thinkpws.txt. From the target host, I execute the following netcat command shown in the CLI to send the output.txt file to my listener. The -w3 flag sets the 3-second timeout after the file transfer completes. I verified that the file was transferred successfully. I now have a custom word list of passwords that think user had stored. Since people often reuse passwords, there's a high probability that one of these passwords is the think user's SSH password. I used Hydra to perform a dictionary attack against the SSH service. Hydra is a login cracker that supports numerous protocols. Let me break down this command. -L specifies username we're attacking with. -P specifies a password list. -V is verbose mode, shows each attempt in real time. ///target IP is the target service and protocol. Hydra will systematically try each password from the word list against the think account. Based on the output, it appears Hydra successfully cracked the SSH password. The password josemario.aka think was in the .passwords file I extracted. Now let's use these credentials to establish a proper SSH session using the command shown in the CLI. SSH will give me a stable, fully interactive shell, much better than my limited reverse shell. After executing the SSH command, it looks like I was able to successfully log in as the think account. The prompt has changed to show think at lookup, confirming I'm now operating with the privileges of the think user. This is lateral movement. I've moved from www-data low privilege web user account to think, a regular user account. Now I can access files that were previously restricted. I I navigated back to the think user home directory. Now that I am authenticated as think, I should be able to read the user.txt file that was earlier denied. Perfect. Based on the cat command output, I can now read the flag in the user.txt. This flag represents successful user level compromise of the target host. But I'm not done yet. The ultimate goal in penetration testing is always to achieve root access. Time to enumerate for privilege escalation to root. With the first flag in hand, I ran the sudo command shown in the CLI to check sudo privileges. The sudo-l command lists what commands the current user can run with sudo privileges. Based on the output, the think user can run /user/bin/look as root without providing a password. The look utility is a command line tool that searches for lines in a file that begins with a specified string. When you run the look utility as root, you can read any file on the system, including /etc/shadow, SSH private keys, root-owned configuration files, and sensitive application data. This is essentially an arbitrary file read as root, which is a severe privilege escalation vulnerability. I ran the following look commands shown in the CLI and was able to successfully read both etc passwd and etc shadow. From the output, I can see the root hash from the /etc/shadow. I attempted to crack this hash using hashcat and John, but it took too long to crack. I decided to look at my options. Knowing that the look utility allowed me to view contents of files with root privileges, I decided to look at the root account's ID_RSA file. I ran the following command shown in the CLI to see if I could access the contents of the root account's ID_RSA file. As can be seen in the output, I was able to view the ID_RSA contents. I'll copy the contents to a file so that I could attempt to authenticate to SSH as root. Before I could use the ID_RSA file, I needed to change the permissions using chmod. On my system, I'll run the following command to attempt to authenticate to the target host as root. Based on the output, it looks like I was able to successfully log in to the target host. At the bottom of the CLI, I can see a hash, which is usually an indicator that I am root. To verify what user I am logged in as, I ran the following command shown in the CLI. The output showed that I am indeed logged in as root. I am in the root home directory and the contents are displayed. I can see the root.txt file, which contains the final flag. I ran the cat command as shown in the CLI and I was able to view the hash of the root.txt file. With that, I have completed this host. To conclude this video, using a variety of techniques, I was able to go from reconnaissance to gaining root privileges on Lookup. Here's what was accomplished. Initial access. I performed user enumeration on the target web application, revealing valid usernames through error message analysis. Successfully brute forced the Jose account password using FUF. Foothold. Exploited CVE-2019-9194 in LFinder 2.1.47, executing command injection through the vulnerable web application to gain a shell as the www-data user on the underlying operating system. Lateral movement. Performed path hijacking by creating a malicious ID binary in the /temp directory and manipulating the path variable. This allowed me to abuse the vulnerable suid binary PWM to extract passwords and move laterally to the think user account. Privilege escalation. Abused the think user's pseudo privileges to run the look binary as root. This allowed me to read the root user's SSH private key and authenticate as root, gaining the final flag located in the root home directory. Thank you for tuning in to this demonstration of the TryHackMe Lookup vulnerable host. Thank you for also checking out the Cyber Overwatch channel. If you find this content informative and you are interested in cybersecurity, please like and subscribe to the Cyber Overwatch channel. If you have any questions, please feel free to leave a question in the comments, or you could send me a message from the CyberSec website listed in the description. Until next time, keep learning. The only way to improve is to keep learning. Pragmatic One, signing off.